Recording is rolling. It's Thursday, March 30th. I have a circuits lab lined up for you guys. Does anybody not have page looks like this? Look at this page. Okay. And so let's hang tight on that. I want to do a quick wrap up from yesterday, and then which is actually a good warm up for what we're going to do today anyway, because you need to use the same skills. So let me put the circuit aside, lab page aside. Okay. Yesterday we were setting up a bunch of circuits just on paper. Okay. Actually, these circuits, you can draw from from this paper to construct some of these today. Right? And yesterday, could use a couple more minutes in class because we were looking at these three in parallel. Let's finish these, and then the calculations we do here are actually going to be useful for your lab today anyway. So it all works out. Okay? So we're saying, well, everybody had different resistors, so yours are different than mine. We figured out the total resistance, did all that. Right? You know how many volts your battery is, minus 12. Right? And then we said the voltage drop had to be the same across all of them because they're in parallel. Even if they're different resistances, that's okay. And so whatever your battery is, just copy paste that number because that's the voltage drop across each resistor. Okay. Now, what is the current going through each resistor, and what is the power consumption in watts? Let's use Ohm's law. So Ohm's law. I'll write it two different ways. Some textbooks write it this way. The voltage drop is the current times the resistance. I usually write it this way. Current is voltage difference acting on a resistor, right? Same thing. Right? And actually, that's the more helpful version for this table, how we're doing it, is V divided by R. So if I had 12 volts acting on 3 ohms, 12 over 3, is that like 4 amps? I think 4 amps. Okay. What about 12 volts on 12 ohms? Is that 1 amp, right? 12 over 12. Okay, that's fine. Okay. And same thing here, 12 over 12. Okay. Which probably makes sense, right? Because we've got this current splitting. I have one resistor that's not very much. So, I mean, if you were looking around town or you're driving around town, right? And you see like 3 stoplights there on that street. You see 12 stoplights and 12 stoplights on each of those streets. Right? Probably most traffic's going to go on the road that has only 3 stoplights. And a little traffic's going to trickle this way. Hey, I have one fat waterfall with like 4 gallons per minute and 2 little skinny waterfalls with like 1 gallon per minute each. That makes sense, right? And then how many gallons per minute flowing back to the pump? 4, 1, 1. Is that like 6? Right? Or you could just do 12 over 2 in my case, right? So it still follows Ohm's law. 12 over 2 is still 6, right? Or 4 from the street, 4 or 1 from the street, 1 from the street. Okay. Of course, those are amps. I'm saying gallons per minute, but I'm talking about amps, right? Amperes. And last column, I can use Joule's law. I gave you guys 3 different versions of this. P equals IV works. You could also do I squared times R, or if you like, V squared divided by R. Okay. Let's say I stick to I times V, current times voltage. I've got 4 amps, 12 volts. Is that 48 watts? 1 amp, 12 volts. There's 12 watts. 1 times 12 is 12 again. Okay. And then this last cell, 2 different perspectives. You could go through the battery. We've got 6 amps and 12 volts. That's 72 watts. Or you could think of it in terms of electricity supply and demand. Because if 48 plus 12 plus 12, that's 48, 60, so that's 72 watts are being demanded. So there better be 72 watts supplied, and it matches. So it's all good. Okay, guys get there? Okay. So Ohm's law and Joule's law, you're gonna get to use quite a bit today. So you guys good so far? All right, let's look at this lab page. So I set you guys up some blank spaces where you can draw circuits. I've got an example here I'll do with you guys. Okay. And I set up these Kirchhoff tables that we have you guys build up. Now you can fill these out. Some numbers you can measure using the multimeter. And then once you get enough numbers, at some point you can just start using Ohm's law or Joule's law and finish off with calculations. Okay. So let's bring back in my example. All right. How to reconnect this thing. It's right there.
Pardon the interruption, but please disregard that up.
There you go. Right. So you guys see it? This is the same thing. Okay. So you can twist these wires together. You can use these binder clips. I do have some alligator clips in the mail, but they're not time for it, so gotta leave that. Right. And so this is this, right? Is that so? Draw a schematic. Right? I've got resistor B and C here are in series with each other, and then resistor A is in parallel with those. Okay? And then I got my voltage source over here. So I draw that. Okay? You come up with different circuits. Here's a bunch of good options right here. Right? You guys can draw something there. Put on at least a couple of bulbs. Okay? Each of these Christmas lights is about 2 ohms. Here, let me show you guys how to get that from voltage and current, though. Okay? So let's bring in the multimeter. Now, if I want to measure voltage, remember I have to look at these 2 leads. Black one, the negative lead, leave in COM. Okay, take out the red lead, put it over here in volts. Switch this toggle. Okay? Now, any of the top left are just going to handle volts DC, direct current, but different decimal places. So I like that decimal place right there. So try that. Okay? And remember how you're going to connect the voltmeter versus the ammeter features of the multimeter. Okay? Remember, voltmeter, you're measuring a potential difference. So you measure, you connect it in parallel. The ammeter, you're measuring current. You have to force the current through the ammeter. So you connect it in series. Okay? See that last couple days? Okay. So let's measure volts across resistor A. Volts across resistor A. I got these numbers from last class, but let's try this again. Make sure this is in frame. Right. It looks good. Okay. Okay. So from here to here, that's 4. I'm getting like 4.7, 4.8 volts. Get that? Okay. Well, that's pretty close to what I got written here already, so I'll just leave that. But I guess it's okay. You guys good with that? Okay. What if I want to get the voltage across resistor B? Would I go from here to here, resistor B? Okay. And make sure this is all on camera here. Okay. I'm getting 2.5, I'll call it 2.5 volts. Goes up and down a little bit. Call this 2.5 volts. Okay. And then across resistor C, it is across resistor C, here to here, that is 2.2 volts. 2.2 volts. Oh, whoops. Where you guys can see it. Well, yeah, okay. 2.2, I'll call it. 2.2 volts. 2.2. Right? Good so far? Okay. Now I just measured voltages. And those numbers look reasonable. That's about what they should be. Pretty close. What if I want to measure current? Current, I gotta make some changes. So pop this out, put it over here. Switch this toggle over to what says MA, like milliamps. I'm just gonna treat this as amps. Okay, amps. But I have to connect this in series, so I have to break open my circuit. Okay. So these bulbs are going to turn off. That's okay, right? Because then I'll reconnect with the leads, and then they'll turn back on. And so I'm thinking maybe I should break open my circuit right here so that I can put my leads like this, bam, and get the current that's going through resistor A. You guys think I should do that? Right. So let me pop off this bit right here. Get this open. Right, so current's still going through those 2, but not resistor A anymore. Back up a little bit here. Okay. Right. But then if I connect right here and right, see where you guys can see the amps. How many amps is this going to be? How many amps? 2.4 amps. You guys say 2.4 amps, right? So, I was getting something different last class. I'll change that. Let's call it 2.4. Scratch 2.4 amps. Okay, 2.4 amps. Okay. I wonder what it would be through these other guys. These other guys, it has to be the same current because they're in series, even if they're slightly different resistances. That's okay. What if I connect it like here and here? I should do that, right? There and there. Get the current through both of those at the same time. Okay. So let me reconnect this guy. Okay. Then, okay, so now we're back to the original. Okay. Then break these guys apart right here. Bam. Go. Red to red, black to black. 1.6 amps. You see 1.6 amps? Okay. So that's 1.6 amps, and that's also 1.6 amps. Okay, you see that? Okay. Now I can use, set this to the side, turn this off, save the battery. Okay. I can use Ohm's law to figure out what is each resistance. So I can switch this around and say resistance is voltage on current. Okay, do that. Put my calculator, because I have a voltage of 4.6 volts and a current of 2.4 amps. So that's 1.92 ohms. I'll call it 1.9. We were saying those are about 2 ohms each anyway. Right, so 1.9 ohms. Looks reasonable, right? Okay. What about for resistors B and C? What is 2.5 volts on 1.6 amps? That's 1.56. I'll call it 1.6. And then 2.2 volt drop across that guy. So this guy's only 1.4 ohms, right? I guess that. And then what about the power? So Joule's law, I could do P equals IV. I could also do this other two, but let's just do I times V. So that's 4.6 volts times 2.4 amps gives me 11 watts, 11.0. Okay. On right beneath it, 2.5 times 1.6. I'm looking at 4.0 watts. And then 2.2 times 1.6 is 3.5 watts. Okay. All those numbers look reasonable so far. Okay. Is that okay so far? Okay. All right. How about the resistance across the voltage source? Let's do what we've been doing. There's different ways you could approach these, right? You could put these two in series. So let's do that. That's resistors B and C. That's 1.6 plus 1.4. So collectively, this is 3 ohms. Now, 3 is in parallel with this 1.9 ohms. So let's do 3 times 1.9 divided by open parenthesis 3 plus 1.9. That gives me an overall resistance of 1.16 ohms. Okay. The voltage drop has to be the same as it was across resistor A, which I was measuring 4.6, right? 4.6 volts. Right? The current total, well, I could do V over R, or I could also take this current and add this current. Either way, let's try that. What's 4.6 divided by 1.16? V over R. This is Ohm's law. I'm getting 3.96. 3.9655. I'll call that 4.0. How about that? Or alternatively, I could add the current from this street to the current from this street. So that's 2.4 amps plus 1.6 amps, which is also 4.0. Look at that. Right, 2 different ways. Right? And then this very last cell, I could do I times V. So that's 4 amps times 4.6 volts, which is 18.4 watts. Right? Now it should be consistent with, if I add these three, it should be at least pretty close. Right? Let's see how close it is. What is 11 watts plus 4 watts plus 3.5 watts? That is 18.5 watts. And I got 18.4 watts using Joule's law. So you guys see how that's the match to? Bam. At least within measuring error, right? Okay, you guys see that? Okay. Okay. Now, who's got questions so far? Okay. Do you guys think that you can come up with at least a couple other circuits with at least a couple of volts on them? Right? And again, you have a whole list of them from the last couple of days. Okay? And then measure voltage and current and fill out the Kirchhoff table. Okay. All right. So once you do that, then turn that to the gray tray. I'll walk around and help you guys out.